Welcome. In this video, we are going to do some problems based on the estimation theory that we have discussed till now. Okay. Moving on, the first problem tells us that a manufacturer of a flashlight batteries claims that its battery will last an average of mean 34 hours of continuous use. Of course, there is some variability in the life expectancy with standard deviation 3 hours. So basically here we are talking about the manufacturer of flashlight batteries, and the manufacturer tells that it will glow for a continuous usage of 34 hours. As an average it will glow for 34 hours, that is what they mean. And it can have some variance, so till 3 hours, that is till 31 to 37, it can vary. That is what they are telling. Okay. During consumer testing, a sample of 30 batteries lasted an average of only 32.5 hours. So the thing is that consumers have bought this flashlight batteries, and they are using it, and their usage is averaged, that is coming as 32.5 when 30 batteries were tested. Okay. Now the question is, how likely is it to obtain a sample that performs this badly if the manufacturer claim is true? So the thing is that we will have to obtain some probability that the sample performs this badly. So we are saying that 34 percentage is 34 hours it will glow, but it is as an average 30 batteries were performed only for 32.5 hours. Now that let us see how it is solved. From the given thing, these are the informations that we have, isn't it? Mu is 34, standard deviation is 3, and the number of sample that we have taken is 30, and the average that we got is 32.5. And we will need to find out the probability that the mean is even smaller than this one. This is what. So the question is, how likely is it to obtain a sample that performs this badly? Okay, so we are in a situation to find out the probability of x bar smaller than 32.5. This is what we are going to find. Okay, generally in these kind of problems, what do we assume? We assume that the population is normal. Okay, with that thing, we will normalize it with mean mu and standard deviation sigma upon under root n. So that is what we are going to do. So assuming the population is normally distributed, and this is what we assume. So we just standardize it. Probability of calculating this thing is same as that of this one. Okay, we substitute the given values into it. Okay, and we when we perform the calculation, we get this one. Now that we need to read the value of this thing from the standard normal table, and the value is coming as 0.0032, which means 0.32 percentage. So assuming the claim, okay, there is 0.32 percentage chance to obtain a sample that performs this badly. Okay, moving to the next question. Here we have n7 random sample from a population. The population has a mean mu and variance sigma square. Actually, that is a typo. It is sigma square, not sigma 2. Now that we are considering the estimators of mu, that is two estimators, theta 1 cap and theta 2 cap given. So theta 1 cap is x1 plus x2 up till x7 whole thing divided by 7, and theta 2 is given like this. Now that we need to check whether they are unbiased estimators. So to check unbiased estimator, what do? We need to find out the expectation of theta 1 hat, which should be same as that of mu. And similarly, expectation of theta 2 hat, that should be equal to mu. If that is the case, we can come to a conclusion that they are unbiased estimators. If they both are unbiased estimator, which is the more efficient? That how do? We calculate the variance, and the estimator with minimum variance is considered as the efficient one. That is the reason. Okay, moving further, this is the given information. So these are the estimators that we have considered, and expectation of theta 1 hat is the same thing. Using the properties of expectation, what can we say? We can have it as expectation of x1 upon 7 plus expectation of x2 upon 7 till expectation of x7 upon 7. From that, this 1 upon 7 is a constant, so we take them outside. Okay, and here these are sample taken from the population having mean mu. So substituting that one, we have this one. So it is 7 times of 1 upon 7 mu. So we get it as mu. So this confirms that theta 1 is an unbiased estimator of mu. Okay, there is again a typo. It is not E of theta 1. It is simply theta 1 hat is an unbiased estimator of mu, since expectation of theta 1 hat is mu. Okay, moving further, now we are going to check for this. In a similar way, if we apply the property of expectation, we get this also as an unbiased estimator of mu. Now we need to find out the variance to check which one is efficient, more efficient. Okay, again, here what are we going to do? We just apply the properties of variance. Okay, and see that it is 1 upon 7 times of sigma square. Variance of theta 1 hat is 1 upon 7 times of sigma square, and moving further, variance of theta 2 hat is the same thing, we just calculate it. Okay, and we see that 3 upon 2 times of sigma square. Now that it is simply half times of sigma square, and it is 1 upon 7 times of, which is that that quantity is smaller than 1, right? Here we have a bigger than 1. So from this too, we are able to see that the variance of theta 1 hat is smaller than that of the variance of theta 2, with which we can come to a conclusion that theta 1 is the best estimator. Okay, moving to the next problem. Here we are given a random sample, n random samples, okay, from an infinite population with mean mu, right? And we are asked to obtain a condition under which this a1 x1 plus a2 x2 till an xn, this becomes an unbiased estimator of mu. So the thing is that here we need to know about the values of a1 a2 till an. Okay, x1 x2 till xn are the random sample that we have taken, assuming these are constants. Okay, we need to find out under what condition this is an unbiased estimator. We know, supposing if we are going to take this one as some theta, theta is an unbiased estimator if expectation of theta equals mu, since the random sample has the mean mu. Okay, so this is what, so expectation of this quantity should be equal to mu, assuming that it is holding. So in that case, we can apply the property of expectation. So it would be expectation of a1 x1 plus expectation of a2 x2 till expectation of an xn. From all those quantities, we can take the constants outside. So it is a1 times of expectation of x1, and the same follows for the other quantities as well. Now that what is expectation of these quantities? These are mu, right? Okay. Now this mu is a common quantity in all the expressions. So we take that as a common and cancel it with the right hand side. So what do we get? We get the sum of the coefficients, that is a1 through an. The sum of all these things should be equal to 1. So this is the condition under which this is an unbiased estimator. Okay, moving further. So now this problem might have given you an idea that when we have a linear combination of the random sample that we have taken, if the coefficient sums to 1, then it is an unbiased estimator. Okay, so not necessary that each and every time when we have something like this in this problem, we don't need to check for that. Okay, here if you look at the coefficients are 1 upon 7 for all the 7 quantities. So when you make 7 times of 1 upon 7, it is 1. So with that thing, here itself we can conclude that this is an this theta 1 hat is an unbiased estimator. In a similar way, if you come here, it is 2 upon 2, that is 1. 1 minus half plus half. Okay, so 1 minus half plus half, which sums to 1 only. Here also the coefficients sums to 1. Therefore, it is also an unbiased estimator. Okay. So, from now onwards, when you are about to work with some multiple choice type of questions, you don't have to really examine everything. if the coefficients, if you are given a linear combination of random sample with equal mean, okay, in that case, if your coefficient sums to 1, then you can very well conclude that that is an unbiased estimator. Moving to the next problem, here we are given that a random sample of size 2n from a population having mean mu and variance sigma square. And here we have two things, x1 bar and x2 bar, that is 1 upon 2n times of summation I runs from 1 to 2n xi, and this is 1 upon n times of summation I runs to 1 times of xi. Okay, we have two estimates. Now that we need to check whether they are unbiased estimators of mu. If you just go through, it is 1 upon 2 times of the coefficient 1, that is repeated for 2n times in the first estimator. Okay, so from this itself, what can we conclude? Just by looking, observing these things, we can very well conclude that they are unbiased estimators. Okay, in that case, which is more efficient. Now, in a typical sense, if we calculate it, this is what is going to happen. Am I right? So in that case, we are going to get, yeah, we can very well prove that they are unbiased estimators. Okay, and moving further, we need to calculate the variance. So when we calculate the variance, this 1 upon 2n comes out as 1 upon 4n square, and variance of this quantity. Okay, this is summation variance of individual, right? Okay, so this is what we would get, that is sigma square upon 2n. This is the variance of x1 bar, and variance of x2 bar is what? We just take 1 upon n square outside, and it is sigma square upon n. So now that what do we have? Sigma square upon 2n and sigma square upon n. Comparing these two things, variance of the first one is the smaller than that of the second one. Therefore, x1 bar is more efficient. So with which we have come to the end of this thing. Thank you.